This unit 5, is the last of the derivative-specific units. We get into antiderivatives next year. This is split into 2 parts. First part is called implicit derivatives. And the second half is called related rates. The second half is calculus word problems. The first half is derivatives of non-functions. Up until this point, we have been looking at functions, explicit equations. Plug in an x, you get a y, right? Like 1. You get 6. But not everything in this world can be thought of using functions. Circles have equations, have feelings, have tangent slopes. Why don't we look at tangent slopes of circles? Why don't we look at tangent slopes of ellipses? Why don't we look at tangent slopes of squiggly lines that are created from this equation, sine of xy equals x plus y? Why don't we look at equations of really cool graphs where it's like a lot of stuff on top of each other going on forever and ever and ever, lots of squiggly lines? Why don't we look at tangent slopes to the thing at the back of your throat? What's that thing called anyway? Oh, okay, good job. I forgot. Yeah, why don't we find like the locations of a horizontal tangents to this, or vertical tangents for this? That's what we're going to be doing, okay? We are going to be finding the derivative of x squared plus y squared equals 9. Now, before we do that, let's just recall when we are finding the derivative. Take the derivative of y equals x squared plus 2x plus 3. Let's find the equation of the tangent to this at x equals 1. We already found the point. You just found the slope, okay? Go ahead. Take the derivative of y equals x squared plus 2x plus 3. Let's find the equation of the tangent line at x equals 1. Okay? Really nice. We already have the point y of 1 is equal to 6. We did that earlier. You plug in an x, you get 1y. Now, most of you, correctly so, had y prime equals 2x plus 2. I really like how you have a left side and a right side. And we know that this isn't the slope, it's a tangent slope generator. You plug in 1 to get the tangent slope. Okay? So my equation is y minus 6 equals 4 times x minus 1. I hope everybody's comfortable with that. If you are not, there's always time to get comfortable with it. Now, what are we finding? Well, we were finding what this y prime, or what we're going to use a lot is dy dx, which is equal to y prime, what that is equal to. All right? And remembering that this whole equation for a tangent slope, this tangent slope generator, that's the beautiful discovery of calculus. The existence of a function that can generate instantaneous rates of change of an equation. Cool. Now, one other thing that you guys didn't do, but you have been doing all along, is showing the step of taking the derivative. You've always been just writing the derivative. But there's one step that you have been doing but haven't been writing, is this. d dx, and then a lot of parentheses around that. This stands for take the derivative with respect to x. Okay, that's take the derivative. And you've been taking the derivative to get dy dx is equal to. Okay, our goal is to find what dy dx is equal to for this equation and for all these other implicit curves that we were looking at. Got that? All right. And our start will be the same as our start for the other ones. We will take the derivative. But then the following happens. We get 2x, 2y, 0. Where's the dy dx? How can I find it if I don't have it? This makes sense to you guys. You guys think this is great, right? Okay. This is wrong. This is wrong. But you're close. We're very close. We could try to do that, but some of these equations you're not going to want to solve for y first. Like you're not going to be able to. Okay? This is wrong, but just by a little bit, and I'm going to show you why. Flip. We already talked about the derivative of y. What's the derivative of y?
1.
No. Look, up here. We talked about the derivative of y. Y prime. Or dy dx. We are going to be using dy dx. It's kind of like using multiplication of these fractions. D times y dx times 1 dy dx. You've already done that. It's not 1. It's not 1 because these variables disagree. Okay? X and the y, we're not going to get 1. So we thought the derivative of y squared was 2y. But it's not. Nope. Watch. I'm going to treat this as a chain. I'm going to treat it as an outside and an inside, just to show you why the derivative is very, very close to 2y, but just a little bit more needs to be added in. If I took the derivative of the outside, I'd have 2 times the inside. Okay, so that's the 2y right there. But then I need to multiply that by the derivative of y. Did we say the derivative of y was 1? No, we said it's dy dx. So it's not 2y, it's 2y dy dx. Now, the derivative of 3y to the fourth is very, very close to being 12y cubed times dy dx. You are exactly right. It's going to be what we think it's going to be times this dy dx. Are we cool with that? And again, the reasoning why is to think about this like a chain, 3 stuff to the fourth, and then y. And to remember that the derivative of y is dy dx if you're taking it with respect to x. Okay? So you can write a little note to yourself. It's just like with x's. You just need to add a dy dx after it. Now, derivative of y, you could think of that as 1, like the derivative of x is 1 times dy dx. So maybe that helps you. Because the y doesn't disappear unless it's like, 3y or 6y or cos y. See if you can take the derivative of 6y and get it correct. It's just do what you think you would do with x's and then add a dy dx after it. Now, we want to probably keep things separate. So just keep dy dx next to it being multiplied instead of as a big fraction. But it's don't erase, you're fine. Now, cos y. A lot of us will actually get cos y wrong because we're thinking a little bit too hard. and we're not thinking about the derivative of cosine x. Is the derivative of cosine x negative sine of 1? It's negative sine x. The derivative of cosine x is negative sine x. The derivative of cosine y, negative sine y times dy dx. A lot of people make that error. Okay? If you have a chain and you'd have to take the derivative using the chain rule, even if it was with x's, you'll have to do it with y's. It's just when you take the derivative of the y cubed, you need a dy dx after. Okay? Root y, 1/2 y to the negative 1/2 dy dx. Okay? Cool. So, go back a page. Go back to the front of the packet. 2x plus 2y equals 0 was wrong. Adjust it so that it's correct. Discuss with your neighbor. What's your adjustment? Two y dy dx is correct. Okay, cool. There's my dy dx that I was looking for. But again, I want a tangent slope generator. I want dy dx to be equal to something. Discuss, converse, think. How can I get dy dx equals something? What should I do? Exactly right. Use your friend algebra to move stuff to get dy dx by itself. That's it. Okay? Now, what's different about this dy dx compared to all the other dy dx's we have seen until now? No, I could write it as y prime equals negative x over y. It's fine. That's it. It's got both an x and a y. We are used to, just like what we did before, just plugging in an x. You know, I find the equation of the tangent at x equals 1. So yeah, I can plug in 1. You need both an x and a y. All right, so let's flip over to, we're going to skip this page, but we're going to come back to it. So you're going to go here. I'm going to change this from a 9 to a 10. And I'm going to say find dy dx at, I can't say x equals 1. Why can't I just say x equals 1 here? Because I get two possible y's. If I plug in 1 here, I'd get y squared equals 9. Well, what y are you talking about, Mr. Mester? You're talking about y equals 3, y equals negative 3. So what you will find, which is nice, is that you will always be given a point. 1, 3. So since I changed this 9 to a 10, 1, 3 is a point on this circle. We can take the derivative, we can find what dy dx is equal to, and then we can plug in 1, 3. And then we could even write an equation of a tangent line. So let's do that. All right, we kind of just showed earlier so I'm not going to spend that much time. We got negative x over y. I plug in 1, 3. I like to put a little at and then the point, and I'll get negative 1/3. Get y minus 3 equals negative 1/3 x minus 1. I did this earlier with the point 3, 1, and we graphed it, and it looks beautiful. Not this one, here. Okay, there's my circle. X squared plus y squared equals a number is a circle. Here's my tangent line. It's awesome. It's really cool. So that is what we're going to be doing. However, most of the implicit equations are going to be a little bit more complicated in terms of the taking the derivative part. So before we go into this one, we need to practice and make sure we're ready for derivatives where we got multiple y's and we got xy's. So we're going to go back a page. Because like y squared plus x squared plus y squared, piece of cake, easy. 2y dy dx plus 2x but x squared y squared is not 2x 2y dy dx. Of course not. X times y, its derivative is not 1 times dy dx. Of course not. Why? Product rule, not quotient. Okay, fine. You psyched everybody else out, though. That was good. All right. Product rule. Ready, set, go. Take the derivative of x squared times y squared. Take the derivative of x times y. Derivative of the first times the second plus derivative of the second times the first. I get that, and I get this. Yep.
So like on the y plus 2y dx and x, do you like cross out the x's and y over 3 or no?
No, that's why I like to say it's like multiplication, but it's not really. Okay?
Does the d like mean anything?
Yes.
Like what is the
You guys know what it means.
derivative?
No.
Change or something?
Yes.
Oh,
What does it mean? Not just change.
Change in y.
No.
The change
A specific type of change.
in slope?
Nope. Why are we using these d's instead of these deltas? Which are d's. This is change, but this is also change. This is the instant change, instantaneous change.
Or is that one average?
And this is an overall change. This is why we say this was like a secant slope versus this, an instantaneous change in y over an instantaneous change in x, tangent slope. So very good question. What does that d stand for? And we should be comfortable with delta overall, secant, d, instant change in y, instant change in x, tangent. Cool? We see, like, it means something. It's slope. Change in y, change in x. It's slope. Cool. We'll find that after next lesson. We're done with dy dx. We're going to look at dv dt, an instant change in a volume at a specific moment in time, a change in position at a specific moment in time. We'll talk about position, velocity, and acceleration, all stuff we can do with calculus. Isn't that interesting? It's going to be great. I know you guys are excited. But let's keep going, because the equation we need to take the derivative of looks like this. So you guys need to be able to take the derivative of x squared minus xy plus y squared. But before we do that, I'd like us to tackle this one, which I think is a little bit easier to explain before we go into the next one. Very good, Mr. Kreth. This is where we just used the product rule earlier, but this one, since it's inside, sometimes people forget about it. Okay? The other thing I want you to be wary of is this minus sign. I'm going to show you how I deal with that minus sign. It is actually different from back in Unit 2. Remember when I talked about baking in constants or leaving out constants? Yeah, some of us do. Okay. I'm actually going to recommend you bake in the negative, so that you prevent this mistake. Watch this mistake. So before I actually get the correct derivative, I'm going to show you the mistake made by almost everybody once. You say the derivative of 2x squared is 4x. You got the minus derivative of 3x. Okay, so I got 3 times y, and I add the derivative of y, dy dx, times 3x. And then I got minus 4y dy dx. This is wrong.
It should be a minus between the two as well.
It should have a negative somewhere for this thing. Let me show you how we deal with this.
Why are you adding dy dx after the y, not multiply it?
I did. Remember product rule. I think we're on the same page. Watch how this will make sure I have the correct signs. 4x plus the derivative of negative 3x times y plus the derivative of y times negative 3x. That's times. Minus the derivative of 2y squared. The difference between my first one and the second one is that this needed to be negative, and now it is. And it is because I baked in the negative 3. Do we see? What is another way you could do it? This is the bake-in method. Okay, let's talk about what the leave-out. Yes, the leave-out method would look like the following. I would leave out the minus 3. I got 4x minus 3. But don't neglect to put parentheses around the derivative of xy. This is the derivative of x times y, derivative of x times y plus the derivative of y times x. Then the derivative of the 2y squared, I get that. Notice, I would have to do an extra step of distributing the negative 3, which is why I don't recommend it. I know you kids like to show as little work as possible and as little steps as possible. So if you bake in, you do not have to do the next step of distributing the negative 3. Cool? Okay, so now with this knowledge, please take the derivative of x squared minus xy plus y squared, and let's make sure we get it right before we now go back to taking the derivative of that equation of an ellipse. You can put a 1 next to the x, and you can make it a negative 1x, is what I would recommend. Nope. Good. So that's 2x minus y. Okay, yeah, that's good. See, like, this is tricky. A bunch of us have gotten it wrong. What's that? Yeah. All right. Yep. It's tricky. If you got this wrong the first time, we're going to do it again. You're going to write this second time. Nope, you made the mistake. This needs to be a negative x. This negative needs to be distributed to that. Good, you got it. But what's the derivative of x squared? Okay, so the derivative of y squared, 2y, dy dx. Don't do the chain rule unless we really, really have to, okay? That was more just a demonstration so that you know its similarity to x's. All right, we should be getting, and this is what I'd recommend you do, and if you did not get it right, you're going to try again. Make this plus a negative x. You get the derivative of x squared. I'd have the derivative of negative x times y plus the derivative of y times negative x. Notice, what most of you messed up on is this term right here, this third term, it wasn't negative. So, start again. Now take the derivative of this entire equation, the same thing, but let's just do it again. What you just did, do it again. If you got it wrong, get it right now. Yes. 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 Coming around this time, we're looking much, much better. Yes. Yes. No. Well, actually, yes. But why do you do the product rule backwards of what I do? It's okay. I'm not offended. Does he do derivative of the second times the first? No. I'm going to have words with him. No, we're on the same page. No, you're good. Okay. We get 2x plus negative 1 times y plus dy dx times negative x plus 2y dy dx. Would you all have equals 0?
Yeah.
Any of you have equals 10?
No.
It's okay if you did. Everybody will make that mistake. Just remember, the derivative of 10 is 0. All right, as opposed to my previous one, the example above, which just had 1 dy dx. It was easy. Subtract the 2x, divided by the 2y. I got 2. How do I get dy dx equals? Please, everybody, try to figure this out. It's different. What should I do? What are our instincts telling us to do? If you follow your instincts, a lot of you will end up where you need to be going. Dy dx is equal to. What's dy dx equal to? You wrote it down on your paper. Have you done this before? No. Okay, good. That's really nice, Mr. Bieber. Follow your instincts, your mathematical instincts. A lot of you are doing great things just by, where did that guy come from? What's this guy? You forgot your dy dx after this 2y. Yeah, get that out of there. Right. All right, Miss Jarrett, what is your instincts telling you to do right away? Yeah, subtract 2x, add the y. Very good. So, dy dx, negative x stays, 2y dy dx stays, subtract 2x, add y. Okay, good. Most of us did that. Oh, we're close.
Did I miss that too?
Mr. Biebrick, what do you think we should do next? Because I got 2 dy dx's. Factor out the dy dx, right? It's just a product. Very good. Some of us were all over that. Now this is negative x plus 2y. Last thing, Mr. Adelarie, what's your last step? You did it correctly on your paper. Yeah, divide the x plus 2y. Negative 2x plus y over negative x plus 2y. Okay, cool. Got that, thank you. Now, who here is taking their pencil, and who here really wants to do this? Ugh, those 2's. Everybody want to do that? Don't do that? Huh? Don't do that. Don't do that. I know you want to. Don't do it. I know you want to think that these x's cancel. Don't do it. It's over addition. You can't simplify over addition. Try with numbers. It won't work. It needs to be multiplication. You do not have multiplication. So that's it. Stop there. If I had a point, I could plug it in. Cool? All right. Trig functions. Implicit trig functions. Squiggly lines. These squiggly lines. We're literally finding the tangent slope generator of this squiggly line. Right? Don't want to be that guy. All right. All right. Take the derivative of this. Let's see if we can do the first step. Actually, I'm going to change this up a little bit. I want it to be a little bit easier. I'd like it to be sine of y equals x plus y. So get rid of that squared and make it x plus y. Just want to get our examples to go in a nice, easy, getting a little bit more difficult, a little bit different. Not more difficult, just a little different so we're prepared for it. Let's go ahead and take the derivative of this. Should be easy. What's the derivative of of sine x? Cos x. So the derivative of sine y is cos y dy dx. Don't forget about the y. It's a common mistake, and it's okay. Okay, this is the first time we've seen dy dx's on both sides of the equation. What should we do? What? Yeah, get them on the same side. If you're thinking subtract the dy dx, yes, that's what we're going to do. Algebraically solve. Put it in my tray on desk. If you're thinking factor out the dy dx, you're right. There we go. Divide. Okay, the next one. You're really going to need more space than I provided, so just please write small. Add another plus y. I want dy dx's on both sides, but I want it to be even more tricky in terms of what we got to do. So, let's start by taking the derivative of sine xy. You guys should just get your phones out and start watching the video from the beginning. Chain rule, right? Chain. So the chain rule for the derivative of sine xy. Write small, we need some space. This is kind of messy.
And do we do product for the x, y?
Yes. Exactly right. Good analysis. Got derivative of sine, but then the derivative of xy, product rule. Okay, now here's where some of us err, is we write y plus dy dx x like this. You are multiplying these derivatives together, you need parentheses around that. So if you failed to put parentheses around it, you need it. Okay, now this is a little bit trickier than the previous one and the one before that. Okay, so we got dy dx's on both sides, yes. We want to try to get the dy dx's onto one side, but I have a problem. This dy dx is inside this set of parentheses, which is being multiplied by cosine xy. I cannot just move it. I cannot just take this and put it inside the parentheses. It's not going to be easy to do. Right? I can't subtract the y. It's inside the parentheses.
You have to distribute the dy over dx.
Or you can do
Yes, Zavio. Distribute the cos x plus y. Very nice. Very nice.
wait, is it cos x plus y or cos x y?
Sorry, it's cos xy. Sorry. Yeah.
Can't you just subtract the dy dx the other side and then divide by cos x y to get 1 over
No.
cos x y?
No. Good question though. Watch. Cos xy times y plus dy dx x minus dy dx would equal 1, right? And you're saying divide by cos xy?
Oh, it's dy dx isn't.
Yes. So if you divide by cos xy, yes, it'd be gone from here, but it needs to be under here and here. Okay? So, good instincts, and whenever you see parentheses and a dy dx inside parentheses, sometimes, depending, you will need to distribute. I get y cos xy plus dy dx x cos xy equals 1 plus dy dx. Now, move your dy dx's onto one side, leave all the other stuff onto the other side, and factor to solve. I'm going to subtract the dy dx. I'm going to subtract the y cos xy. I'm going to factor out the dy dx. I'm going to pause right here, let you catch up. Factoring out the dy dx from the dy dx. Don't neglect to put the 1 there. Got the right side. And then I divide. Okay. Messy, huh? Yes. Lots of steps, huh? Yes. Lots of places where one little mistake can snowball on us. Yes. Even if your x's and your y's start looking like each other, like you can make a big mistake. So make sure your x's look like your x's and your y's look like your y's, or you might mistake something. You have to be very diligent taking these implicit derivatives. So you have to practice and be careful. Pay attention to the details. All right. We kind of did this one already. We found equations of tangent lines. And I'm going to just quickly get through this so that we can get into the tougher derivatives. I'm going to bake in this -3. I'm going to find just dy dx. We did stuff like this already. So let's find the equation of the tangent line. Bake it in the -3. I have the derivative of -3x times y plus the derivative of y times -3x. That's equal to 0. I can subtract the 2x, add the 3y. Make sure you're using algebra when you're doing this. And then divide by the -3x. We can plug in 1, -3. I like to put a at 1, -3, and I get -2 plus -9 over -3. It's -11 -3rds, which is 11 thirds. All right, so I get my equation of my tangent line y plus 3 equals 11 thirds x minus 1. Great. And graph it, look nice. This is like a hyperbola. I think it's like rotated or something. Cool. But reminding us about last unit, we can take this and use it to approximate points on this implicit curve. So if I ask you, hey, use the tangent line to approximate k, it's just what we did last unit. We will be plugging in 1.2 for x. I'm going to be finding k, which is a y. So k will be approximately 11 thirds, 1.2 minus 1 minus 3. Probably don't want to take 0.2 and multiply it by 11 thirds, right? 2/10, 1/5, 11/15. (3/45)15. (-34/15). That's our approximate k value. Okay, tangent line approximations. This is not new, just showing you it's the same as last unit. Okay. I'm literally going to skip this equation of the tangent line and this tangent line approximation just so we can move on. I don't think it's necessary. Look at that. What else did we do last unit? We talked about logs and e's. Well, we have implicit equations with logs and e's. I think this one's going to look pretty crazy, huh? Log x minus log y actually is lame. I don't even want to look at the graph. But I'm going to anyways. It's that. Boo. I want something like that. Something's going on over here. I feel like it's going up left, up right, and then curving over. So that's why it's not a function, because it's gonna, but I need to zoom in, and I don't have like Wolfram Alpha Plus to be able to zoom in. So do you guys know about how great Wolfram Alpha is?
Never heard of it.
Oh, wow. It could take any derivative of anything. It could answer lots of questions using a lot of data. My favorite thing to do is to type in people's names. That's got to be surname, I think. Yeah, you're 46th in America for
Popular name?
most popular name. 1 in 744 people have that name.
What name is that?
Carter.
What's number one?
I don't know.
Now, is that female or male?
That's a good question.
Oh, good luck. Emily?
A lot of 14th. Yeah, boom. This is what I like to see. They will show the overall popularity of your name through the course of U.S. history. So back in the day, yeah, super popular. You're at the peak right here. Yeah. Now it's coming down. Yeah, not as cool. That's my dad's first name. Okay. All right. So Wolfram alpha. It's actually really, really powerful and really cool. It could tell you the derivative of log x, but you know it. What is it? 1 over x. It could tell you the derivative of log y with respect to x. What is it? It's not 1 over dy dx. Good. 1 over y, just like 1 over x, but then times dy dx. And then we'll solve for dy dx. That's funny. Maybe you move the dy dx's over to the right side. Divide to solve. Okay. Now, if you were given this question right here, you should just plug in 4 and 4. 1/4 plus 1/4 over 5/4 is 1/5. Great. But if you were not given this question and you were asked to find the tangent slope generated of dy dx, you might not see this. I will show you some simplification that you may be expected to do. So, how can we simplify 1 over x over 1 plus 1 over y? We could add these together by giving this a y over y. And you got y plus 1 over y, and then you can kind of flip and do that. That's totally fine. My instinct is to multiply the top and the bottom of this entire expression by y. It's just multiplying by 1. And watch how we'll get y over x over y plus 1. It's pretty much what we'll get if we combine that 1 and the 1 over y. And then my instinct is telling me to multiply the top and bottom by x to get rid of the x in the bottom, giving me y over xy plus x. You might need to simplify when you have fractions inside of fractions. I've seen on the AP test, they don't like fractions inside of fractions. They like you to simplify that. So be ready to do that. Do they like decimals? I don't know, sometimes. All right. Let's try this one out. Find the derivative of log 2x plus y equals x plus 1 at 0e. So let's do the first step, because I'll show you what we can do. Using the chain rule, O's and I's, making sure you are multiplying the derivative of the inside with parentheses, we have this. Now, in the past, when I had a dy dx stuck inside parentheses, what did I tell you to do? Distribute. It's mostly because I don't have a dy dx on this side. I don't have to distribute. I could now divide by the 1 over 2x plus y, but that's the same as multiplying by 2x plus y. So why don't we do that instead? Multiply both sides by 2x plus y. Giving us 2 plus dy dx equals 2x plus y. Subtract the 2. Okay? We will find that the next one, we got to find this at 0e. So dy dx at 0e, e minus 2. 0.7182818.
Do you know more numbers of e or pi?
I think I know more numbers of pi. I just know 3.1415926.535. How many do you know?
I forgot a lot. Like, I just know over 100.
Really?
Yeah.
Oh, cool. Was it a contest?
No.
I know middle school teachers sometimes have like contests for who can memorize the most. Yeah? And who won? No.
In 6th grade, we just had a pie day at school, and all the 7th graders were out on a field trip, so it was like the 5th, 6th graders in the math class or whatever, and so we spent all 5 days doing a big pie.
And so how many do you know?
I used to know like 50 or 60.
Wow. Cool. No, I just know 5, 6, 5, 3, 5. All right, let's get to this one. This one will be a little bit more difficult because of the dy dx on that side. Go ahead, take the derivative. Very similar to the last one in that you'll have 1 over 3x plus 4y times the derivative of 3x plus 4y. Okay. Can I just multiply by 3x plus 4y? Nope. Because I got a dy dx on this side, I got a dy dx trapped inside. We're back to distributing. Got to combine them. You don't need the dy dx there. I don't know why I put it there. It can be on the side. Ready for this one? Yikes. I'm sure we could have done something else. Actually, yeah. I probably would have multiplied by 3x plus 4y. I probably would have, because I could have had 3x plus 4y times dy dx equals 3 plus 4 dy dx. And then move it around, and I end up with this. It's nicer than distributing. A lot of different ways to do this. It would have been easier, actually, if I did it that way. All right, so logs, last unit. What else did we do last unit besides logs? Ease. Might as well throw an e to the x in here. What's the derivative of e to the x? So what is the derivative of e to the y? Good. Dy dx. So it's not e to the dy dx, it's e to the y times dy dx. You get the cos-x, you subtract the e to the x, equals e to the y dy dx, divided by the e to the y. You get cos-x minus e to the x over e to the y. Two more. We might finish early. Yep, that's next class. Yeah, we'll keep it simple though. Two more. Here we go. Find this derivative at 0, 1. I got the first step up there, so if you want to check after you do the first step. Negative e to the negative first. Cool. Last one. You see a lot of these xy's thrown in because they're tricky. Everybody forgets that they're a product and you have to use the product rule. So go ahead and
Did you use the product rule and then multiply by dy dx again?
No. The derivative of the outside is e to the power. The derivative of the inside, you use the product rule. So you have the dy dx inside the parentheses. So go ahead, O and I it. O, I, e to the power, xy, e to the power. Get e to the xy. Y plus dy dx x. Minus 2y dy dx equals 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 equals. What is equal, Mr. Pana? 0. What? 0? Why isn't it E? What? E is just a number. Tricked you. E is just a number. This is just a number. It's not e to the x. It's just a number. The derivative of the number is 0. Okay? So don't get tripped up by that. It's just like if I asked you to take the derivative of pi. It's just 0. Now it's different because like we haven't talked about like pi to the x's derivative. What's the derivative of pi to the x?
ln
X. X to the negative. Oh.
write it out, but it's
She's got it.
pi ln no.
Pi to the x,
Yeah.
natural log pi. Mm. All right. What do I do now? Yep, we distribute y e to the xy plus dy dx x e to the xy minus 2y dy dx. The dy dx is free. Subtract the y e to the xy. Factor out the dy dx. Notice these are involving a lot of steps. But it's what we need to be prepared to do. At 1/2 2. Sure, we'll leave it like that. We did it. We're done early.